Okay, cool. I think most of us are here, so I guess we can get started. Hello, guys. Thank you for joining us today. Today's session is centered on computational design and simulation tools. Okay, computational design and simulation tools for centered around the idea of biodesign. And we're gonna start with a presentation from Dana of one of her works in the masters and also on the use of some Houdini tools. Okay, I'm gonna leave you guys with Dana, who's starting to share her screen.
Hi, everyone. Welcome back to our workshop. Very happy to see you. So today is day 2. The topic of our conversation is computation and the simulations. And computation and environmental simulations are crucial for biodesign processes because they enable, modeling and anticipating and projection of biological systems, allowing designers to understand and predict how organisms will interact with their materials and the environment. Today we'll go through very quickly some of the Houdini tools, Grasshopper tools, and Autodesk CFD tools. Houdini and the Grasshopper node-based coding parametric modeling tools, and the CFD is a simulation tool. Yes, so this is towards bioreceptive facades for algae growth is one of my boosters project at the Bartlett School of Architecture. I created a system of panels to enhance algae growth in the urban spaces. As you know, in the urban development, the greening of metropolitan areas has become a central focus of the design, and the greening is usually defined as Ken, I think we should maybe perhaps mute other participants because I feel like someone is talking to someone. Yeah, thank you. Yeah, there are several architectural designs that incorporate plants and other photosynthetic organisms you perhaps have seen in your cities, green walls, to create mainly for aesthetic reasons, but also passive. It can reduce the heat islands. It can filter air pollutants, reduce atmospheric CO2. So those are the main reasons why in cities we can see green walls. Yeah. However, one of the reasons why it can be, let's say, problematic is because to create green wall structures, you need a lot of plastic structures. So, and also for water piping, you need plastic, and also it's quite energy intense. And therefore, in the past few years, a novel technique has emerged in the green walls systems development. And this approach is called bioreceptive walls, roofs, facades, and envelopes. So it includes what is bioreceptive. This is how it's usually defined, is the aptitude of a material to be colonized by one or several groups of living organisms without necessarily undergoing any biodeterioration of the structure or the material. So one of the reasons this approach is significant is that it shows a big promise in tackling some of the inhibiting factors of current systems. As I mentioned, it also is a passive system, and it doesn't require any soil. And if you are growing like moss, organisms like moss, it doesn't have a root structure to deteriorate or destroy the material that you are using. Yeah. Therefore, we came to a conclusion. It's very important to create establishing a cyclical procedure. As you can see, this is the iterative process between 3D modeling. You can use from Houdini, Rhino, Grasshopper to Blender, 3ds Max, to fabrication tools. And in this case, it's digital fabrication, CNC milling, and robotic 3D printing. But you can as well use low-tech fabrication methods like slip casting methods, or weaving, felting, and so on. And other environmental simulations. You can use both physical tests, whether it's at home or in the lab, and also solar analysis, heat transfer, weather analysis. So this was a very cyclical procedure for us. My goal was to create green wall systems for chlorella vulgaris. It's a species of green microalgae that is widely grown across the world. You probably have seen it. It sometimes creates this kind of like film on the surface of water. It grows pretty much everywhere. It prefers temperature between 25 and to 27 Celsius, ideally. And it also prefers intense sunlight. It can grow also without any sterile conditions, so it's very resilient to the environmental inputs. Yeah, so as you can see, today we're going to teach you how to use height fields in Houdini, and this project is fully utilize height field tools. And you can also use simulations to understand where we can have the sunny areas exposed to the sun, shaded areas, to understand where your algae might grow. The morphologies, the inspiration came from geological morphologies that's shaped by wind, sun, and water over time. This is Cappadocia, my visit to Turkey, and I think this is from Google, but it is a tide pool in the UK, a fascinating space also that creates micro pockets for diverse ocean organisms. The modeling starts from like plain height field grid, and then we will also show you that you can create a noise to create a randomized surface or controlled surface, more or less. And then you can use painting tools to mask where you would like to alter, manipulate. And in this case, I wanted to have a terrace. And this is the final first iteration of the panel that I used for using height fields. And this is the preliminary modeling options. As you can see, the various, you have unlimited options to create macro and micro textures for your ecosystem. And this is a CNC milling tests that we have done at our workspace, BMate. And then I did physical water tests, and based on the physical water tests, I looked at how to adjust my wet maps. So I created a script in Houdini that imitates rain without wind. So it was very interesting to see how it was very similar to the physical tests, and therefore we can approximate where the wet places will be. And therefore, like, this is approximately where algae might grow. Yeah, here are some of the renders. Yes, based on this information that and learnings, how water flows on the surface of the first geometry that I showed you, a few adjustments in the geometry was made. As you can see, we wanted to even out the water flow and also decrease the speed, so slow it down, the velocity of the water. So here are the few other iterations that I have done. And then I also simulated in Fusion because we used CNC milling. So in Fusion 360 software, you can simulate how your CNC milling will go in the toolpaths, and approximately get how your geometry will look like after the CNC milling process. CNC milling means generally removing the material using computer-aided data. It's very accessible. It's everywhere in the world compared to 3D printing. So yeah, based on this, we also saw how the micro textures it would create as a result of the fabrication, and therefore this would create an additional space for algae to grab onto. And here is the result. as you can see, this did not turn out as we expected. So next iteration was also like water test, and it was very different from the geometry that I had in mind. And the third iteration of the form generation was after several water tests, we came to a conclusion that the water runoff is fairly quick. And in order to maintain the growth, we need to create additional water pockets for water and nutrient accumulation. Therefore, we export Voronoi structure using grasshopper and Houdini. And these are the pockets that we designed for algae growth. This is a scene simulating process. And the fabrication process was very challenging. Unfortunately, whilst working with other material, was dense foam, that we only had dense foam in the workspace. We did not use wood in the beginning. So we failed to take into account the materiality and limitation of wood. So the proposed design for this piece was excessively thin, resulting in breaking of the wood, as you can see. But somewhat unintentional lesson that was one of the most important lessons that we took away was it would create these textures, and that would increase the amount of surface the algae can attach to, which is great because this creates micro textures for our microorganism. So the final design consists of two sides, terrain-based surface and water pockets, as you can see. The front and the back side was informed by Voronoi. One was informed by a Voronoi structure test that I have done, and the back side was informed by the height fields. And this is the wood gluing process. And this is the front side and the back side. These are the micro textures, and we also took into account what we learned from fusion and from a few of the failures that we had. And this is a really interesting process. So we designed in height fields and then simulated in Fusion. And this is the physical object of CNC piece. Then we 3D scanned it, did the wet map test. It was quite similar to the digital test that we have done. Therefore, we can say that even with bigger panels and bigger structures, we can approximately say this is where the wet parts will be. So this is without wind, again, the rain analysis. And then we did solar analysis, solar radiation analysis of London, Gatwick, 4 seasons, 1 month each. And our model organism is chlorella, again, microgreen algae. And we know that it likes from 25 to 27 degrees. We also know that London is very humid with an average amount of 86%. So which can be described as humid but cool in October, and December has the highest relative humidity, 97%, and least humidity in July at 71%. So we can approximately also see when would be the highest amount of growth per year in algae on our panel. Yeah, so this is the renderings of algae colonization in 40 days. Based on the data that we learned from simulations. And terraces creates a preferable surface area for algae colonization, whereas water pockets create a space for water and nutrient accumulation, therefore providing a space for other organisms to colonize faster. Then the next test was heat dissipation. We took a hairdryer and we looked at how heat dissipates and distributes in 5 minutes. And this is just a dry panel, and this is soaked in warm water, and you can see the difference how it dissipates. In this was 15 minutes time, and this was 5 minutes time. So at the end, we learned so much about the wood, the material, and heat dissipation, and also we thought how algae might grow. And another question that we had was, can we integrate robotic fabrication to this process? So can we create panels that also have 3D printed attachments So 3D printed, why is 3D printing? 3D printed attachments can act as an additional design tool for extreme environment conditions, such as excessive heat during summers, drought, or cold winters, balancing the temperature due to its materiality. So yeah, you can design a panel that is like, standardized, for example, and you can send out to the locations, even like 2-3 cities in your country, and you can adjust the design based on the environmental simulations by 3D printing additional surface. So natural thermal properties of timber also maximizes the efficiency of insulation materials, as wood will not become cold or dissipate heat quickly, therefore requiring less energy to maintain warmth throughout the facade, which is preferable for our organism. Whereas clay blocks are unique in offering high thermal insulation with equally high heat retention properties. So it can also increase the amount of surface area for algae to grab onto. So this is 3D scan of a physical model, and this is a rendered of 3D printing design. And this is a digital, how it might look over time, and this is a robotic fabrication. 3D printing clay onto wood, which we have not done in our program. And of course, it started cracking. This is post-fabrication process. Yes, so I learned a lot personally. And then we did the same test, a heat dissipation comparison, 5 minutes. So as shown below, the fired clay attachments helps to redistribute heat across the surface fairly quickly compared to the wooden panel, which is, very useful during hot summer days. Yeah, so this is the final image. Humid shaded areas can be colonized by moss, for instance, after algae, and exposed to the sun areas can be preferable more for microalgae, and the 3D textures can create extra surface for other organisms, such as algae, to grow, and water and nutrients can accumulate in this pocket. Yeah, thank you so much. And this was my project in one of the semesters at Bartlett. Yeah. So today we're going to learn height fields. How does it clay stay on wood when especially it's dry? It was fired. It was fired and glued to wood. Does anyone have questions about this process before we start our height fields?
How is it doing today?
How's it doing today? I actually don't know because I left it in London in our studio.
You didn't leave the video camera on it and have somebody checking it each day?
Yeah, I should have. I agree. Is there a simulation tool for heat map to simulation tool? I think CFD might have heat map. Correct me if I'm wrong, Edward. But
I'm not totally sure. I believe it does, but I'm not aware of that one.
Yeah, if you have standardized material, it would be easier if you take the material and actually get the hair dryer and scan it. So you can also download heat map apps, I believe in App Store or Google Play, and look through so you will see how it dissipates over time. Is there a tool about heat and sunlight in water? That's a good question. I actually don't know. Heat and sunlight.
I think you would just treat it separately. You would check the heat of the water and then check the sunlight patterns and then evaluate weather conditions with it.
Yes, thank you, Chris. Was there any difference in terms of microorganisms that would eventually latch on wood panel versus clay panel? So clay, when it's fired, loses its porosity. It depends how you fire it.
Yes,
If you glaze it, it
are also
will
okay.
completely lose its porosity. I think we
Can
need
you
to
mute Fatima?
mute our.
Yeah.
Normally, this is so tiny particle.
Can do you want muting our? Thank you so much. So in versus like wood, if it's not laminated or there is no additional layer of resin, it would attach very naturally. So yeah, the porosity and how much water it can hold is defining property, like yeah, for microorganisms. Okay, great. It seems like no one has questions. Great. Okay, let's have fun and learn height fields. To do so, we need a Houdini Apprentice. Could you please let me know if everyone downloaded Houdini? And if you could open Houdini Apprentice, that would be great.
Then I think somebody raised their hand. Maybe there's a question.
Oh, yeah.
Hi, am I audible?
Hi.
Yeah, Bala here. So
Oh, Bala,
I
hey.
hi. I had one question. So one of the slides from the presentation, it was showing how the panels were digitally fabricated using CNC milling. So how did you optimize the surface or the micro textures which you are showing when it comes to digitally fabricating using CNC milling? Because I can see that the CNC milling contour levels were having constant values, like each level had a constant value. The micro textures, I mean. So where it was said that it was ideal for organisms to grow properly. So does it have any proper optimization that has undergone?
So based on our algae research that we have done in our lab, and I have done with my colleague Junior, we know that it likes microtextures. So based on that knowledge and scientific papers, we looked at approximately the microtextures and the sizes and macrotextures. And also we learned, we read about wood and algae, which would it like, and so on. So yeah, and the microtextures were created and controlled by mainly height fields, which I will show you in a minute. So it's more of, you have to just test it more and see whether your organism will grow. So it's actual work in the lab or at home where you have an organism, you try to grow it, provide nutrients, and see if it grows. And there is a really good startup in Netherlands called Urban Reef. They 3D print clay, and they fire it, and they still leave some porosity. And they look at how it will be colonized in urban spaces in the Netherlands.
Okay.
I don't know if I answered
one more
your question. Yeah, absolutely.
One more question. So
Bala, sorry, I can't
another
really
slide
hear
shows
you.
that.
Sorry, you have
Am I
some.
audible right now?
Yeah, it has like, it's not very clear, but yes, I can.
It's not very clear. So I think I'll type the question in the chat box. You can answer it later, maybe.
Bala, did you ask a question? Sorry if I'm.
No, he said he was gonna type it out because it's hard to hear him.
Okay, perfect. Thank you
Yeah.
so much. Yeah, perfect. There are a few questions. I wanted to ask about the installation. Is it product build or daily build for production build. What do you mean, Muhammad? What do you mean by daily build and the production build? I didn't get why did you put clay on the surface? It was, we wanted to use multiple materials to see what would be the difference between wood and clay. And also, like, if you have a standardized panel that was a sort like from usually made in, you know, China or, you know, in Europe, you can import your panels and adjust your panels with 3D printing. It doesn't necessarily need to be clay, but it's an interesting idea that we don't need to have universal panel systems or tiling systems. We can adjust it depending on the environment and climate using 3D printing. So this is something that we wanted to explore. When I try to install, you should open Apprentice. It's free and it works perfectly unless you want to render it. Could project utilize a structure similar to coral reefs, which offers more 3D space for growing algae? Yeah, absolutely. So today, in terms of like coral reef-like structures, Edward will going to teach us how to create branching systems. And I'm going to teach you how to create more flat surfaces, which is great for wall planar surfaces, yeah. So we have today two parts. One is height fields. For those of you who would like to create modular tiling systems or anything that looks like landscape or tide pools, and those of you who would like to create 3D volumetric branching systems or coral reef structures, simplified, Edward will teach you how. And then we also have CFD simulation part and the solar simulation part. So this is going to be a very intense day. I'm curious if you have conducted some sort of life cycle assessment study. Yes, we did, but our life cycle assessment study is a little bit different because we have a different framework in biointegrated design. We believe in, you know, regeneration, biodiversity. So the material can provide food for the next organism. So our life cycle system is slightly different. It's more towards regenerative material systems. Algae simulation, 40 days. How did the morphological addition of algae was possible in any software? Could you please explain the parameters that constitute algae grows? So, okay. I would say I can share it again. So how I did was I read papers on algae growth, and we know that our the model organism is Chlorella vulgaris microorganism, microgreen algae, so we know that it likes exposed to sun spaces. It likes 25 to 27 degrees. And we know that humid and shaded places are preferable for moss. Yeah. And we know that it likes microtextures based on the research that we have done. So those are our parameters. So we need to create pockets for water and nutrient accumulation for it to have, you know, nutrients. We need to create microtextures that are exposed to the sun for microalgae. We need humid and shaded places, pockets, for moss, yeah, for moss and water. So therefore, the design was informed by that parameters, and whether it will grow or not grow, we cannot say 100% because there are lots of environmental inputs. Yeah, there's not only sun, wind, rain, and and heat, temperature. There is also like human influence, air pollution, water pollution. There are animals. There is also like the quality, the CO2, the particles in air. So we cannot control fully how this is going to grow unless it's in the lab. And even in the lab, you can never control a biological agent 100%. Yeah, any synthetic biologist will say to you that. So we have no full agency, but we can control the environment and nutrient. But if it will grow or not, it's actually is something that we can also only project. Yeah, especially if it's open spaces. In the lab, yeah, we can say where it will grow approximately based on the research. But yeah, this is how it is. So this is based on the somewhat degree on the research, and also understanding like the organism where it might grow. Is there a model where you would harvest the microalgae? So thank you so much, Bala. If I understood you correctly, to harvest microalgae, you generally to grow microalgae, you need a bioreactor. So it is a sort of like vessel. It's a vessel with air pump, water pump, and if you pour nutrient and algae, you can grow algae. To harvest it, you need to just sieve it. Yeah, with a synthetic nylon material that has very, very tiny pores. So you have to sieve it. So this is how you do that. In terms of on the surface of the material, you can just, take a knife or something. Okay.
Dana, maybe we should start with the practical part in Houdini, because we have a lot of things to go through.
Okay, great. Okay, can you guys let me know if everyone opened Houdini? Great.
I think it's okay to get started.
Okay.
Yeah.
Great.
Also, don't worry if you at some point feel that you're not following at the speed that Dan is going, because Dan is still gonna share these files so everybody can have all of these scripts that you can work with. So we're gonna share these files at the end. But yeah, if you can follow her, amazing.
Amazing. Okay, this is very exciting. I'm excited to teach you height fields and Houdini. So Houdini is a 3D tool, 3D modeling, 3D animation, and visual effects software developed by SideFX, and it was mainly designed for game designers, VFX artists, mainly for cinema, animation, and the gaming industry. However, 10 years ago, 15 years ago, our tutor Javier Ruiz, who teaches at ECL, he actually thought that architecture needs more procedural tools besides Grasshopper, Rhino, Blender, and so on. And he started using this video gaming tool essentially in his architectural projects, and it became very popular within the university. And this is how Bartlett started using it. Until today, it's very encouraged to use for architecture and design students especially in our program, because it creates very organic shapes. It can create lots of options for you to create textures, micro textures, coral reef structures, branches, and so on. You name it. It's fractal-like structures. It's really fun. And Houdini is interface has shelves, as you can see on the top side and on the left side. Yeah, so the most important side is on our right-hand side. It's a network editor software. So the primary workspace that we work will be here. Is everyone? Okay, perfect. Yeah, everyone is on. Yeah, so it's a node-based software. It's non-destructible. So let's create a node. To create a node, you just click right. Yeah, and you will get a tab menu. And you can type height fields. This is the name of a node. Yeah. Blue color selected. If you want to deselect your node, you just click and your node deselects. Yeah, if it's big like this, you can just press Tab and G. Yeah, and you will see your object here. Okay. Okay, so this is information also important. Yeah, inspect. Here you can see what it contains. Yeah, your node. This is a node/folder, because if you open your folder, you can have lots of nodes. So it's a network as well. It's non-linear network, meaning that you can always go back and change your nodes, delete your nodes, add nodes, and you will be able to change the direction of your object, how it's developing. Okay. So the viewport, you can see here, you can have wireframe bounding box, you can have shaded bounding box, wireframe, hidden, madcap shaded, yeah, flat shaded, flat wire shaded, smooth shaded. They're all here. Let's stop at madcap shaded for now. Also, you can show all objects, ghost other objects, hide other objects, yeah? In our case, let's just ghost other objects. You can have single view, 4 views, 2 views, 2 views side by side, 3 views, yeah? Single view, 4 views, it's up to you, however you like designing. And left shelf, yeah, displays different tools, mainly transforming tools. Yeah, this is move, T, rotate, R, scale, E. This is handle, and this is attachment. So we don't need these tools for now. So just use T, rotate if you like. These are the very basics. Okay, is everyone okay for now? Okay, great. How can we change the background? Okay, great. D, background. So this is D is for display options, world view, color scheme, dark, yeah, or gray if you like. Okay, so we select dark, save as default. Excuse me. Any other questions? G, and what's the longest keyboard? I forgot the English. Between Alt and the Alt Control usually. Just a second, I will say. Spacebar, yeah, spacebar G. How do we display these details? What do you mean by details? How did you add objects again? Okay, sure. So we click right on our mouse and we text height field, yeah? So today we don't, oh, okay, so we also have timeline here. We will use timeline a little bit. This is to simulate erosion. We also have shelf. We're not going to use any of the tools here. We're just going to use mainly this side of the interface, the right side. That's all. Any other questions? Okay. All right, let's do it again. Height fields basic theory. Let's create a height field. Yeah, so what is height field? Height field essentially is flat volume. It's not a mesh, and there are no points, edges, or vertices. Yeah, it's important to understand that the height field has resolution, which can be determined by grid spacing, which is here. The smaller the grid spacing is, the higher the resolution is. Okay, I'm gonna read your message at the end. Let's go through height fields a little bit, and then we'll
Yeah, I'm
stop.
gonna answer where I can. Just go through the lecture, and I'm gonna help out
Okay.
in the chat.
Perfect, perfect. Yeah, the size dictates overall the size of the height field. Yeah, so grid spacing is here. So height field is flat heights. Yeah, hence the name height fields. So we can only control height and the mask. Yeah, those are the only two things that we can control. There are no points, primitive vertices, and volumes here. So if we want to select your node, yeah, if you want to work and see what's happening, is you can just select, yeah, there's the blue, the last thing. Just select it. Okay, so there is the initial height, and you can also create initial mask, yeah? So the maximum the mask is, it means like you are fully selected the whole geometry as a mask. The lower it is, the lower is the mask definition. Okay, so this is grid spacing. If we, right now there's, it was 400. As you can see, this is 500, sorry, 1,000 voxels, yeah? So 1,000 means this is 1,000 voxels, units, Houdini units. It's similar to meters. So this is 1,000 meter to 1,000 meter, let's say. Yeah, if we want to change it, we can change it here. Yeah, we can make it, for instance, have a different size. Yeah, so you can. All right, let's go through the. Let's create a height field pattern. So you right click, add height field pattern. It's a fun way to create a texture. So a lot of you would like to create modular system for your site. And for that, it's really fun to explore this tool node called height field tool pattern. And there is a lot of like, you can also select height field or mask. Yeah, in this case, let's select height, and I will go through mask a little bit later. You can blend the height, add, yeah, subtract, difference, multiply, maximum, minimum, and blend. Yeah, so this is how the noise of the pattern applies to your grid, essentially. It can add, it can multiply, differentiate, and so on. You can also choose how to blend it. Yeah. This is the height of your pattern. Yeah, you can control it here. This is the base height, so the height of your grid. This is the blur. Let's go a little bit closer. Yeah, so 0% blur is star-like. Yeah, and the higher you go, it actually gets absolutely blurred. And this is again a grid. Yeah, so you can choose different pattern types from RAM. Yeah, it's a stair-like texture, to steps, stripes, cells, stairs. Okay. You can also rotate to create a structure. Yeah, you can change the size, obviously. You can scale it. Yeah. You can scale, let's say, you can change, so you can change the center. Yeah. As you can see, this is moving. You can randomize the pattern. Yeah. You can rotate the shape. So those are for randomization, all these tools. Yeah. To distort the pattern, you just select the distort on this node, and you can choose between curl. As you can see, you can add noise and distort the shape. Yeah, so those are other tools. I'm not going to go very deep into this. You can play around, and the file is shared with you. Another way to distort your geometry would be height field distort node that you can also add, right click, height field distort, and you will select. Oh, I forgot to say that, yeah, you have two nodes. How to select them is you click and you drag the line to the next one. This is how you connect them together. If you want to cut the connection, you can actually select it and delete. Okay. The second dot that you see, the first one is the main information. The second one is it's a geometry. The second is for input, mask input. Okay, so if you have a mask, you can input to the second. Okay, distort. These are the natives that I'm showing you, but there are also like there are a few things I wanted to show you how to add image as a texture base. Yeah, we also created new textures, but it's just very complex with Vex. We decided to not teach you today because it would take just too long. How did you create patterns? Is height field patterns. We're using what Houdini is providing us. Height field patterns, yeah, it's here, guys. Okay, great. Is anyone enjoying it? So this is one way to create height field pattern. Okay. Okay, great. So you can also use height field resample node to change the resolution of the height fields if you don't like the resolution that you see right now. To do that, you have a height field resample node. Yeah, I'm using a different file here. Yeah. If you want to change it, you just add resample and you know, play around with resolution scale, and you will just find whatever fits your goals. Okay, so you can remap the values from black and to white. Okay, I'm gonna show you. So we have a file. Yeah, so we can include a picture to our height fields. Yeah, which is black and white, which I'm gonna show you, I think. Yeah, this is the image that I input. And this is how it's going to look like. Yeah, with height field file. You can remap it. Yeah, so what is remap? So you can change the values from black to white to a new curve. So this is a remap. So if you go right click, again, height field remap, you will see this node, and you can remap between hill, linear, round, smooth, steps. Yeah. So if you'd like to adjust the remapping tools, yeah, you just adjust it. Yeah. How do you add image? We're going to share the file with you. If you go here, yeah, you can add here. I'm gonna select it red, but we're going through a better node. I'm gonna show you a better node. Yeah, so remapping tool is really interesting because you can remap the values, yeah, and have desired morphology. Okay. So someone asked, how can we add an image? So this is an image that I added, which I'm going to show you in a second. Textures. I think this one is. This is the image that I have. Yeah. So this is the height field file. You just have to add your texture here. Yeah, reload the texture. Yeah. And you can just put the size, the scale. It's not really important. Just input the texture that you really like. And then you can blur it. Yeah. As you can see, height field blur. It's called right click again, height field blur. And you can blur however you like. Yeah, some nodes allow you to load information from your computer. Can you explain again? Of course, yeah. Okay, so we're going to share the file with you. I mean, even if I believe it's already shared. So you have to select height fields file. Yeah.
Dana, can you maybe show them by loading a different picture to this node? And they can see the change that different inputs can have on the height field.
Okay. Okay, let's do it again. Height field file. Yeah. So to this, yeah, you have this, you click this, you select an image that you really like. Let's say this is my image. Oh, this is just not big, but essentially I have to transform this, but you have to add, we're going to share the file. The images that you are uploading are tiny compared to the landscaping tools of height fields. So Kenneth, can you remind me if the files are shared? Can we share with them now? So they can, because some of them are transformed to the scale, landscaping scale.
Yeah, it's there's a drive folder where you can load all of these files. I'll send you a link on WhatsApp. And yeah, the link for all the participants, it's on the Miro board. And I can also send it to the chat right now. Yeah,
that would be great. Because we adjusted a lot of tools to the scale of height field grids. Okay, whilst it's kind of sending you the link and you're uploading link, let me go through this. Yeah, once you have manipulated your height fields, you can re-export them as height field height map image, useful for diagrams and drawings. You will see these nodes in your Houdini file. Also, a lot of people import into Unreal to create a landscape. Yeah. Okay, so you can remap the values as we discussed earlier. This is the value that I really preferred. But if you'd like to because it works only in height and mask, you cannot unfortunately manipulate, this in 3D volumetric way. But we can definitely work with heights. So therefore you can remap it use the default remapping tools like Heal, Linear, Sharp, Smooth, Steps, yeah, Valley. Okay, great. So if you're having a hard time right now to apply a texture to your height fields, we adjusted the size, so therefore I would suggest you to download the file and open it with me, so we can go through the file again. Thank you, Ken. Okay, meanwhile, everyone is waiting. Height field noise is an important tool. Yeah, let's create a height field. So you have a height field, it's a grid again. Yeah, so if you would like to create a noise, yeah, texture, we don't have day one, no. So, okay, back to height field noise. So you can add procedural noise that you can control anytime. And to create terrain like, terraces like, tide pool like, yeah, there's infinite numbers of textures you can create with height fields, which is just incredible. As you can see, height field noise has height and the mask. Yeah, you can mask them, you can use the height. Let's use height for now. The combined method is add for now. You can create different amplitudes. This is the height of the amplitude. Element size. You can scale it as well. You can offset it, yeah. So this way you can create various type of textures for the tools that you are developing at the moment. You have various noise types, yeah, from sinusoid, Berlin, sparse convolution, Berlin flow, periodic Berlin, yeah. You can also offset your noise textures, yeah. Create roughness, yeah, depending how rough you would like your textures to be. You can also rotate. Also, there is an incredible post-processing tool called Fold and Complement. It sort of inverts your textures. Yeah. So okay. All right, let's go back. Let's go back. Has everyone opened the file that we shared? Okay, great. If you have any problems, please text in the chat, we will help you. So how to create, so this is a volume that exists only in Houdini. Also, you can open it in Unreal Engine. But if you really want to export it to a mesh, how do you do that? You add a node called Convert Height Field. Yeah, it's right here. And you add your, from the output to input, yeah, to convert height field node. and therefore you will have a mesh. Yeah, this is a mesh, polygons, essentially. If you have a very heavy polygon, you can check it in information. Yeah, this is 9 megabytes, 49,000, which is not bad. Sometimes you get millions with height fields. So if you have that case, try to take it and poly reduce it. Right click, poly reduce. What does it mean? It means that we can reduce it. Yeah, we can reduce the polygons. So this is the percentage to keep. Yeah, you can see how this is transforming. But please note, if you have a high amount of polygons, like millions, which is very much possible in Houdini, not possible at all in Rhino, you have to decrease it by 10 and 10%. So from 100 to 90, from 90 to 80 to 70, you cannot go from 100 to 5%, which will totally crash your computer. So yeah, have fun. Please add your textures here. Look at and try to explore height fields, and we will go further. Next one, how about if you would like to change the shape, you don't like the boxy grid shape, is the rectangular shape. You can remesh it again to change the resolution. Yeah, to change the boundaries of your height field, you can create a geometry like sphere, and you can do Boolean. Boolean is a very traditional 3D modeling node tool. So you have one object and a second object. You can displace it, you can add it, you can sort of combine it. Yeah, so this way we can, oops. Yeah, as you can see, this is how it's displacing. So we have this, yeah, and we are booleaning the difference between our grid and the sphere. And this is what we have. Okay, great. Okay, I will be very quick. If we have time, we can come back and explore more complex tools. But right now, let's go through this. Let's say we have a shape that we imported from Rhino or made it in Houdini, Blender, 3ds Max, doesn't really matter. How do we import that to height fields? Yeah, so we want to create micro textures onto the shape that we created elsewhere. To that, we will use test geometry. Yeah, peak head, very funny. It's one of the geometries. You have also Monkey and Johnny in Houdini as a test geometries. We transform it. Transforming is a really good tool to transform objects. Yeah, so let me just show you quickly. So if you need to, for example, you have an object, yeah, you created something in height fields, but you would like to copy and transform it 100 times, let's say. Yeah, just let's think that this is our design. You can create a total number right here, 100. Yeah, you can translate it, meaning transform it. Yeah, so like let's say 100 points to X direction. Wait, is it? Oh, no. 100 points to X direction. Yeah, and rotate 2 degrees. As you can see, procedurally, you are able to create 100 copies of peak head in 2 degrees rotation. Yeah. So this is a great tool if you would like to work with rotation, copying, and so on. So we have a peak height for our height fields. How do we apply to our height field grid? First and foremost, it's very small. Yeah, landscaping tools are gigantic. So we create a transforming tool node and yeah, multiply it to 100. Sorry, uniform scale would be 180. Then we add height field project. Yeah, as you can see, it is added as a mask. Yeah, the second input. So the peak head is transformed, increased in size, and added as a mask. So your objects, you can add it as second input as a mask. And once it's on the height field, you can manipulate it by blurring it, for instance. You can play around with blurring. Yeah, you can barely see it was a pic. You can use blurring multiple times. You can remap it, of course, again. Yeah. You can distort it. You can add height field, let's say noise. So let's do height field mask by feature. So we can mask your object by its feature. What a tab menu. Yeah. So we can here select by slope, by height. Yeah, we can do it manually, or we can just compute range. Yeah, so it will select the maximum height and the lowest height. And the mask, you can select whether you want the lower part or the higher part. We can also select by height, yeah, by curvature, by direction. As you can see, these are the vertical directions. Occlusion. Oops. Yeah, let's select occlusion for now. And we can add to the noise. Select the noise. Noise layer mask. Wait. Yeah. So here we go. Like with if you input the mask to first and second input, you can play around. If you would like only the red part to be selected, I actually will show in the second. Yeah, like this. As you can see, you have to select only the features that you would like to be manipulated, yeah, to add noise to. Is that clear to everyone? Because we would like to show the last script that we have. Can you change the orientation of height field being on top? Do you mean the noise or the height field? The features comes from the node, yeah. So we have by slope, we can select. Here you can select, right? You can also select the second node, noise, yeah, while changing this node. Yeah. Sorry, this node. Mhm. Okay, great. Don't worry, if you have the file, you can follow. You can play around with nodes. I know this is very quick. It seems like the field on the top of the head. Can you do it where it's from the side? Yes. So if you have like, you can actually, I think, remap it. Height field mostly feature.
I guess you could also rotate the head, right?
Rotate the head. Exactly. That's the easiest answer. Okay, so let's rotate the head. Okay, rotate.
Yeah, and
Monkey.
afterwards, whatever geometry you get from the height fields, you can also rotate at your own,
Yeah.
volition.
Yep. Yeah. So as you can see, this is the side because we distorted so much. This is how it looks like after lots of noise and distortion. Okay, guys, we have very little time. Let's go through 2 last scripts that we have. So we have height fields again, yeah. And we have a noise. This time I wanted to create a terrace like height field. Here we can see that combined method is add. Amplitude is higher than the element size. The scale is slightly different. You can also use different noise types here. Yeah, so in my case, it was periodic pooling, and this are the preferred the settings that I preferred. You can also fold it, yeah. So if you'd like it to be inverted, you can fold it. You can also complement it, which means another inversion, yeah. Okay, so I wanted to show you the painting tool. Yeah. So let's reset strokes. So you have a shape that you approximately like, but you feel like you would like to create a microtexture to the shape, right? To do so, we can use painting tools, which is great because it's manual. You can control more. You can be very creative with it. Height field paint. And how do we paint? Is you press enter. Yeah, here we go. The red brush with the scroll in the middle of the mouse. You can start painting. Yeah. Okay, so as you can see, this is very intense red color, which means that this is masking 100% the geometry. Yeah. If you'd like the value to be different, it's called FG value. Yeah. So as you can see, the red is less intense. Therefore, the mask wouldn't be 100%. Yeah.
Dana, I'm just gonna do a quick clarification. What Dana is doing right now is not painting for the sake of giving color to the geometry. It's being used as a mask. So the position and the intensity of the paint is gonna be a guideline for other parameters to be applied. So this is gonna effectively change and affect the geometry. It's not gonna give it a color shade or something like that.
Yeah, absolutely. It's just a masking, painting for a mask, yeah, masking tool. Okay, here we go. The places that were red. So for those of you who doesn't have a file, let's create a height field terrace. Yeah. So you select the node and you use compute range. So the place that we painted, the masks, yeah, the red part, the intense part, got lots of steps, terraces, and less intense was the paint. As you can see, got very, very little steps, yeah. Okay. And let's blur it. We can clear the mask as well. Yeah, here's how our design looks like. And convert the height field to polygons. And then extrude volume to close the shape. Yeah, if we want to change the size of the volume, it's here. Sorry. Yeah. As you can see, this is a panel. Yeah. Okay, is everything clear with this part? Because I'm moving on to the next.
Also, just to mention that this is being recorded, so you guys are gonna be able to watch the recording and, you know, go with it at your own pace. So don't worry too much if you didn't get every little detail.
Yeah, absolutely.
You can set the units in the properties, but yeah, it's basically when you're working with the interface, it's working with the units that you set. So if you set 1 and you set the units to be inches, it's going to be inches or meters or millimeters and so forth.
Yeah, but Houdini is not precise like Rhino. It has its own unit systems. In height fields, it's similar to meters. I think 1 voxel is 1.2 meters, if I'm not mistaken. So yeah, 1,000 to 1,000 grid voxels are almost 1,000 to 1,000 meter, but it's not. Yeah, it's not precise. Okay, the last section, very fun. We created height fields. We painted it completely red. Yeah. Then we added noise. So specifically for this workshop, we wanted to work, some of you wanted to work with tide pools. So this could be perhaps one of your departuring geometry. We can also change the noise depth, yeah, element size. We can, because it's still painted, we can create a terrace. Yeah, as you can see, we can arrange the terraces. If we want to create micro spaces, textures, we can also use remapping tools. It's here. Yeah. I think we can also change the step size. Yeah, it's here. Let me make it slightly higher. Okay. And we clear the mask. This is our shape, right? And if you'd like to see how this might look like, just to see the patterns of erosion, let's use a height field erode. Yeah. Essentially, it's a simulation tool for erosions, and this is highly used in cinema and VFX effects. And you can probably see like how the wind flows, how time goes. Usually it's used by Houdini. Also, I would like to also highlight that Houdini is used by astrophysics and a lot of scientists because you can input very precise mathematical formulas to Houdini. And if you know how to code very well, you can have very precise scientific visualizations using this tool. Okay, so erosion. We can select the node and see how thermal and hydro erosion happens over time. So each second in the animation is, I don't know how many years, probably like 100 years or less. But overall, erosion is a tool to see how in hundreds and hundreds of years your landscape might look like.
So I think, sorry, Dan, I'm just gonna comment something here. I think the mindset of how the program was conceived is also important, because this is a program that was designed for people who were doing movies, who were doing video games. So they were probably not very concerned in precision, but they were concerned in being able to produce very complex shapes very fast. So for that, Houdini is very powerful. And it is a very interesting tool when you're trying to produce biologically inspired geometries and shapes that are usually also very complex.
I think I can piggyback off Ken real quick and say also that it's important what Donna's doing, because in the program, the mindset is to show degradation, erosion, show the product over time, instead of just producing something and then saying this is final. The program is very much focused on what happens over a long period of time. So the Houdini works well for that kind of stuff.
Yeah, absolutely. As you can see, the geometry is eroded, is being eroded, you know, with temperature, hydro, and wind, and so on. It's great for a lot of you who asked about material aging or material simulation, erosion simulations. I think this is a great tool that is often overlooked. Yeah. So here we go. Okay, great. So in terms of erosion, you can also select only one erosion tool, which can be a hydro or thermal. Yeah. You can just decrease the amount of rate. Sorry, I can't do this because it will start simulating again. But if you'd like to try only thermal erosion or only hydro erosion or precipitation erosions, you can adjust the settings here. Yeah, there's also water flow, debris flow, different iterations, water absorption properties, the height, the global seat generally, riverbank, yeah, all these tools are here. Please have fun, look at it. Also, you can visualize, you know, you can change the colors of the visualization. Yeah, my favorite is Inferno. Yeah, it's just loading. Can you say specific time frame? Like, I want to know. For that, I think yes. So you can give, you can understand how long is 1 second, yeah, per frame. Yeah, So you can calculate, I think, using, try to Google height fields erosion time frame. And based on that, you can, yeah, you can develop the scripts further. Okay, great. One more tool that I would like to show you is, so we have a shape that we like, let's say. We can blur it. This one. Yeah. And then we can also look at height fields, flow field, and look at the general precipitation patterns, yeah, or where the water will accumulate. Oops. Yeah. So this is great for those of you who are looking at where the rainwater will be collected, or where the, you know, where the flow will happen. So yeah, this is great to generally design in when you think of that. Okay, does anyone have any questions? Other ways to set a camera and export this result images? Yeah, so there is render flipbook. You can export that, and also rendering is pretty straightforward with Mantra. You can set up Mantra fairly quickly. Okay, let's convert it to polygons. Yeah. Sorry? Okay, great. So this is a very, very introductory 20 minutes. It has been 20 minutes. Please, yeah, just to take it as an exercising tool. We would love to see your results. And now I'm going to give the presentation to Edward, actually.
Yeah,
Yeah.
if there's not any last minute questions for Donna, I can move over to branching. There seemed to be some general interest that people wanted to do more three-dimensional modeling in Houdini, so I figured I could toss this in real quick for today. I made a simplified version that everyone can work with, so that it's a bit clear and you can get something like this fairly quickly. So I'm going to go into Houdini if everyone's ready. Can you guys see my screen okay? I don't see the chat. Okay, cool.
Yes, we can see it.
Great. So real quick, I have two different types. So the first type is branching using scatter points, which means you can make a branching pattern within a mass. And so it's interior solids. And then there's branching using surface wrapping, which is the one I'm showing right now. I'm going to start with scatter points, and then through that, you'll understand the surface wrapping, because that one's much more simple. So in Houdini, as Donna showed, you can import your own files and objects using a file node. So with hers, it was all height field files, but in this case, you just use a general file node, and in the properties, you would then just import. But for the sake of simplicity and speed, because these files can get quite heavy, I recommend using a geometry node. So if you do create, you can create simple geometries here. And in that, then you'll be able to see that it's like general shapes that you can use to make objects. So I'm using a torus just because it's a more interesting shape and shows off the branching a bit more. So the way this node works is that it goes through kind of a branching and then reconnecting, it'll scatter points within a solid. So first Houdini has to understand that it's a empty object. Not that it's not an empty object, but that it has mass. So this ghosting is it understanding that this is an interior surface. And then through that, you can scatter points. If you select a node, you can see that you can force the amount of points in it. So varying complexity affects, you can affect the complexity of the branching through that. Then what you do is you need to have an object that the points become. So these scattered points all need solids that have additional points within them. I use the sphere that I had transformed and flattened. And so it copies those. And these all become locations where you can select points within it. As you progress forward, you can see that there's, it selects those points and then connects the connections across them. But this is not shortest path quite yet. The way this works is that it is just making all connection points. And you can, if you see here, the search radius and max search point and max connection are crucial for this node because you can choose how far they reach. So if I were to reduce it and reduce the max search points, let's see, there's always a happy medium. So you can see how it starts finding, it gets quite sensitive when it's small, but it starts reducing the amount of points and reaching range. And then also the max connections affects how dense it becomes. And then just some simple transform, you're fusing the connections for smoothing, and then it gets into the shortest path, which starts making connections not just generically across, but instead is finding literally the shortest path amongst the members. So in order to make the branching also kind of a cleaner process, you can polyframe it, which smooths it. And then the attribute map is where you start adding the thickness and adjusting the scalability of it. So if you want the branch to look realistic and kind of tubular, it starts going from the input max is like the smallest and the output max is the thickest. And then you can also do some final reshaping through the offset. And what that does is it, in between the gaps of the connections, it'll offset along here. So let's say if I make it 3, it makes it less like more linear connections instead of being like kind of rounded out like when we had it with 5. So converting it just simply makes it an object that is readable by other programs. So convert DVB brings it into a realistic object instead of like a Houdini mass. So that was kind of a really quick crash course, and the nodes that I emphasize are the ones that are important for controlling parameters. I left notes here for you guys if you want to mess with it, and I recommend sticking to geometries for now because it's very easy for an object that you import to take up to 30 minutes for it to load a branching system at the final result. It's just, it gets extremely complex. The difference, you can see the difference here versus this one is, this clearly has objects within, but this one is hollow. So you can also do surface wrapping and branching. The color is just for you guys. You can modify colors of nodes for just yourself for editing. So if you know that you have this huge script and you are not aware of, or that there's many that are doing things but are not parameters that you can modify, you can just either label them or not label them, however you like. It's a personal choice, and it's in here. All these tools in this bar are helpful for like basic organizing. This is how you create sticky notes. This is how you create the network box that you see that I have. And whatever you have selected is where it will build a box. You can have boxes within boxes. You can, when it's in there, you can move it all together with the header. So that's how I often organize my scripts into one file, because it helps with just, sometimes the scripts get super crazy and dense. And so you want to be organized in any way possible. For this one, instead of scattering points, all it does is take the surface wrapping, the mesh grid. In this case, if I had not done the remesh, which I'll show you real quick, the remesh is just a way of modifying the grid so that it's a little bit more interesting. I'm going to use the yellow skip to skip that one, and I'll show you now the result that what's happened. So if you notice, the lines are here, and when I convert, the lines are in the same location. So you can modify the way that it follows the surface based on how you remesh. So it'll follow that grid. So this one is more simple. All it does is grab the surface, it groups it, and then you can select within the group how much percentage of points you want. And then just run through finding shortest path, making the polyframe as I showed before, making the VDB, which VD means turning it into the solids. And then in this case, this one's not going through the attrib map, which is the scaling. It just has the same same thickness, but you can affect it if you'd like here. But yeah, that's a really quick crash course on the branching structure, and it's a really simplified version of it that I think it would be good for if you guys want to do somewhere three-dimensional or even planar. This one's effective for planar. But yeah, I think I did that pretty quickly. If there's any questions, let me know. Can you easily Boolean at the end? Yeah, Boolean is a command that you can do at any point. That one is and what's nice about Houdini versus like Rhino, for example, is that you can Boolean very fast. So if you notice, see if the pink, it shows so the blue shows the actual object, the pink shows a shadowed version of it. So it's not rendering this out, it's just giving you where it is. So if you notice the tiny little box here, it's too small. So what we need to do is scale it up. And usually like 10 is the max, and you want to just have to type the rest. So let's do like 40. And 60. And you can also move it. There's two ways to modify this thing. So you can either click and type, or you can press down on your center mouse wheel, and then there's varying levels of intensity, and you can just slide over with the mouse. So I'm just sliding left and right. And then when I run the Boolean, it'll cut out a chunk from that part. And it makes it solid. And if you want, you can visualize this one and show that one and work here. And if your computer can handle it, you can do it as you're moving, so you understand what you're cutting. But sometimes, like I said, the branching structure, I'm using a very simple object with a low amount of scatter points. Unless you have a strong computer, I don't recommend putting in your own geometry yet. I think just using the create geometries would be fine. So if I replace this with a torus, with a box instead of a torus, and just let it run, now we have a box version of it. I think the increasing points really affects the look. Yeah, you can boolean at any point. So let's say I don't boolean here, but I boolean even in the beginning. So let's bring it back to the torus. So we went through there first and then there. And then visualize the plant. Actually, sorry. Yeah, that's okay. I'm gonna find the cube. Because it was running at a scale that was transformed further down. So just to talk about that real quick. I mean, there's nodes that you'll see are skipped or occur later in After Effects. Often it's better to transform earlier unless you feel like there's a size issue or it's like too large of a file, because then you can render things out through the program and then transform it based on where you put it. Like for example, this blast here that I had skipped, what that's doing is if it's too complex of a system, if you add this blast back in, it'll cut out a huge chunk of the polyframe randomly, and it'll then become a more simple object. So going back to this, I just want to see. So yeah, giant box, tiny thing. So we'll bring it back to 1 because they should be at the same scale, and recenter this. Now, when we run it, it'll boolean out the cube inside there. And then same deal. Now you go through the process and it'll just do branching within that space.
Thank you.
Yeah, so I think I recommend, so someone asked about exporting as STL. I think I recommend first exporting as OBJ, bringing it into Rhino. Through the past for me personally, I feel like bringing it into Rhino helps with, you can clean the model and you can make it, I feel like Rhino makes better STLs. But that's just through my own experience. Everyone has their own kind of workflow. I often just bring these into Rhino as OBJs. For exporting, you do save geometry, and then you want to select a folder. You can put DigitalFutures, and then you have to put the file name in 2 locations. So you find OBJ and you put .obj and you accept. And then just to really hammer it down, because sometimes it doesn't do it, you select it there too. And so it'll now give you that. And then if you go here, you see it's there. Bring it into Rhino and you should be able to just open it as a mesh.
It's funny because that 3-hit method for the file type, like I've done it too. It seems paranoid, but for some reason, sometimes it doesn't do it. So you just
You
triple
just have to
thread.
do it. Yeah, like it's gonna be this file type. Don't fight
Yeah.
me. Like, and so yeah, then now that you have an OBJ, you can quad remesh it and clean it. Let's say 2000. Which this might take too long.
Yeah, this
But
is the
yeah,
kind of operation that Houdini does much faster. But
exactly.
yeah, at some point in the process, if you want to 3D print it or fabricate it in some way, it's probably going to still pass through Rhino or Grasshopper.
Yeah.
Yeah. Have you poly reduced in Houdini at?
Not yet. I can though.
Yeah, that would be, I think, faster actually.
All of these polygon reduction operations, Boolean operations, BDB operations, copy to points operations, those are much faster in Houdini.
Mhm.
But Rhino is still useful for a lot of things.
So yeah, then in this case, I don't need to go through the whole process, but yeah, you would just export STL and then open it in whatever 3D printing program that you want to use. In our case, it was Cura. Let's see, any more questions, guys? This file is in the drive also called branching, and it's pretty streamlined. But if you guys have any questions after and you want to work on it, just let me know. I can help with it.
Are you
Cool.
going to save this updated file?
I could. There's not many changes. I added a Boolean and a poly reduce. If you want, I can. That's no problem. I think for sake of like clarity and cleanliness, use the first one, and then when you understand it better, you can use this one. Okay, cool. If everyone's good and they feel comfortable, I think this is a good point where we can take a 10-minute break. Grab a coffee and chill for a sec, because after this, now that we're done with Houdini, we're going to get into some simulations. I'm going to start with CFD and just explain that kind of workflow. And then Ken's going to start talking about solar analysis. So I think we'll be back at 6:10. How's that? Cool. All right.
Cool.
See you guys in a bit.
There we go.
Okay. I feel like I should start going. So cool. You guys have seen a lot through Houdini. You understand how to do a lot of model making through parametric process, but now we're going to get into analysis. I'm starting with CFD. CFD is good for wind flow, but can be used as water flow in one direction as well. So the main interface before you load a model looks like this, but once you load a model, then the setup there's important keys that you guys are going to be using primarily. CFD has a lot going for it, but this is going to be a very simple, clean cut description for it. like I'm gonna handle just one singular process for CFD, and this is the one that I use and the one I know best. From here, I would need tutorials myself. Um, let's get started. I'm gonna show you guys how to do a water flow analysis. So the first thing I'm gonna show is how to load a file. You select new, browse, and then there's two types that are work best for CFD. There's IGES and there's SAT files. So if one isn't working, you can go ahead and use the other one and it might work better. So this is an IGS file. And you have to name it as well, because what it does is once you make a file and save it, it'll make a folder where it packages all the elements necessary for CFD. So I can call it DigiFutures test1. And then there's other options, but create is the one that actually helps with analysis. So I had modeled this through SubD and Rhino. Typically for CFD, what happens is that the models get really complex and often crashes or never loads. So I highly recommend if you're going to model something in Houdini, the next step is to then have it modeled and do a simplified version of it in Rhino so that you can actually load it and do analysis. So maybe just one portion or one part. And I can show you an example. So I was working on these branching structures, but I wanted to see how dense they needed to be in order to actually have effective wind flow blockage. So this is a simple geometry I made in Houdini, I mean in Rhino, that is just layering branches, and I analyzed layers one by one in rows until I found the one that I believed was the most effective or had a method that or an amount that was not making a difference after a certain point. So you get results like this, which I'll explain all that and show you how to get to this point now with the other file, the more simplified one. But you guys can get something like this. It's achievable fairly quickly. So now going into this model, so we're fresh. There's no bounding box, nothing. It's just the IGS file that I brought in. So you need a bounding box for it to actually have the wind flow through. You can either model it in Rhino and then select the material based on it, which I'll get into that, or you can do it within CFD. So if you select geometry tool and exterior volume, it actually creates a bounding box that you can modify. But since this is a very tight panel-like analysis, you want to keep it to the frame. If you select these arrows, you can drag it and make more space, and maybe you want flow to occur more around the object. In this case, we're just going to create a tight bounding box and close that out. So now the way the material works is that you need to define what it's colliding with, because otherwise it's not going to be a realistic analysis. So just for some basic, because CFD has its own way of navigating, this is, so you can hold the center wheel and shift and drag to rotate, but it's a little bit clunky, and I actually recommend using the box in the corner for navigating around the model. It helps just keep things kind of linear, because at some point you're going to end up like upside down with the model and you're like, how do I get back? And then center click and control is how you make things disappear, and you click the same thing away to make it reappear. When you select objects, you just need to click once and it'll select it. So now we're going to edit the bounding box's material. You want it to be a fluid. You can choose between fluid and solid. There's lots of options, but again, I'm going through the main things that we need to focus on for this lesson. So it's a fluid, and fluid is technically, air is technically fluid for CFD. So that's what we're going to do. So now we've applied the box as air, and so it won't collide with it when we do the analysis. I'm going to control center click the box so I can access the object. And we're going to do edit. And this one, we're going to do a solid. And let's say we do, there's lots of really interesting, great options. You can do concretes, clays, metals. Let's just say it's a dry clay soil. So now we have the materials set. And if you look here, it says the materials are set. It shows here the materials that are available in the model. And it doesn't say anything is unassigned, which is important. If you don't have something assigned, it'll recognize that and not solve the script. Now we're going to go through the boundary conditions. This is important for choosing the direction of flow and how things flow through. In this case, when you select boundary conditions, then you can now select certain faces. And the reason for that is because you have to define where the wind's coming from, what is just like the wind tunnel, and where the wind's coming out from. So I'm going to center click on the surface just to check something, which is which direction do you want? The object's going this way. I want to flow from this side. Again, center control click, and now I see the main box. And the box is what determines where the flow comes from. So I will single click to select that face, edit it, and then we're going to go with velocity at meters per second. And this is the main source of where the wind's coming from. And for the velocity, 25 is extremely high winds and 1 is like a light breeze. In this case, since it's a panel and a small scale environment, let's say 5. You can estimate and kind of find something that's a happy medium. Sometimes it's good to do really strong ones. Is it possible to define a vector for it? Do you mean the direction?
So usually,
Yeah.
the direction, the vector of the wind is perpendicular to the surface that you put it at. But if you want a wind flow simulation that has a direction that's not perpendicular to your volume, you can just rotate your volume. But usually the box that you use as a reference works on perpendicular vectors. What can rotate is the geometry inside.
So we've just chosen this first phase. So this is the direction that the wind is going this way. And now we need to select the second phase. Something important that I need to mention right now, so people don't make the same mistake, is I had selected this phase. And if I select this phase, it doesn't mean it doesn't unselect that one. So you need to re-click that one in order to then modify it without layering parameters by accident. So once you get used to the color coding, you'll know that black is set for velocity. On this side, what you need is pressure, which is literally just a pressure force that pushes through. When you apply it, then it's a light brown. And then the rest needs to be the wind tunnel for the bounding box. So we're going to select all around, edit, and then just click slip symmetry. And that's blue. So now the boundary conditions are set. Nothing needs to be set with the model. It's literally just defining the boundary. Mesh sizing, which is what this is that it needs to read, and it needs to analyze the object in clusters, because if it does it all as one, it becomes too complex. So if you auto size, it'll automatically make connections of clusters and be able to read data individually amongst the entire model and calculate it. So now it's essentially set up. So you're prepared to do a wind flow simulation, or water flow in this case. So you hit solve, and then you want to do 200 iterations. It just has more effective results. And then just select it. It'll go through the process. Sometimes you get error messages for whatever reason. Maybe there was something not selected right, an unassigned material. Sometimes the model's too complex and it can't handle it. There's lots of interesting ways that CFD figures out how to crash. Like even just putting the boundary box around the object from CFD it'll just crash. And so you might have to just either retry and it just ran out of data maybe, or try a different method like making the boundary box in CFD. So right now what it's doing is going through every iteration. It's doing it in a parameter of centimeters per second. But if you right click this and hit units, you can modify that and choose which yeah, what's up?
Could you hide a couple of faces of the box so we can see how it's running the iterations on the geometry?
So right now it's just going to be solid until I set it to what was it? Static pressure. So there's two ways to show results. Well, there's a lot of ways to show results. The results, by the way, for the question is they're really accurate. They give you based on the wind flow speeds and the chart that you follow, you can get really clear understandings of flow. So yeah, the options here, there's lots of different ways. You can do a global thing, you can do a single plane cutting through, you can do trace lines. I like to do trace lines because it's kind of a way to show it in a water flow method, and also it just is an interesting method for visualizing. So it completed it. By the way, I selected output bar to reduce that. And now we have the general box handling the pressures and flow. If you want to view the object inside, click view, and you could do transparent. And then now you can see everything that's happening. And in the results panel is where you can start adding and removing different types of results. So for example, if you want to put traces that flow from one direction to the next, what you'll want to do is keep the global setting because it needs a surface that it can apply onto to keep it linear. So you select on this face a linear view, you select traces, and in this case you can modify the density and the way that it does it. So I like grid because it's clean. Seed density, since this is a smaller object, I can show you real quick. So when you select add, you see this is the points. It gets really hard to see inside the model, but if you look closely, there's a little line here that is going to make traces. So if I click again, and then you see how the lines can increase, so you can have that many lines, or if you're doing water flow, then 1 or 2 is best, and it'll create it across the object. And then same deal as before, if you control center click, you can hide the global box and be able to see the traces. So you know how the flow goes across the surface. Also the forces on the object. And there's some ways to modify it to where you can clean up and visualize it more easily. So let's say, for example, real quick, I'm going to remove this. I'm going to re-show the box with center control click. Go back to the face. Just add a new trace now with 0.5 density. Just so that we have more lines. Just so you can visualize it better, but the colors are distracting. So center control click for that box to remove. You can right click the model. Instead of showing results, you can show a color. Just select white. And now it's very easy to see the forces across the object. Along with that, there's a lot of things on the field that are a bit distracting and maybe you don't need them. So if you go to view and go here, you can turn off all these conditions. And now you have a cleaner visualization. I think someone needs to mute. So the color is the intensity. So the pressure of wind forces. So as it goes across the model, you'll notice that it goes from red to blue. and the red is the strongest force. And then as it goes across, as it's impacting the model, it's slowing down naturally, and so it becomes blue and it goes past. So you can, what's up?
Sorry, quick question. Could you show us how to edit the boundaries of the legend? Because it has happened to me that I have run more than one simulation, and then I get the colors, and then I figure out that I had different boundaries for the legend, so the results weren't comparable.
Do you mean the units or the range?
The range.
Mm.
Well, and the units as well. I think you can set that up when you're gonna run the simulation. I think it was on the column on the left.
I haven't actually done that. So you're saying in the results when you do the solve, you can modify the boundaries?
Yeah, so yeah, and so you see on the column on the left, it says scenario 1. I think if you right click on top of scenario 1, you can set the bounds of or I it's something there, and you right click. It has to do with the actual simulation. Oh, it should be in the solver down there. It says solve.
Maybe in the results.
Yeah, no, definitely in the results. Definitely in the results. I can you continue. I can actually figure it out while
Yeah,
you.
because I haven't messed with that one.
Yeah. No, it's
but it's a good point. Let's see. So what else do we need to cover? And yeah, so if you mess with the global results, because typically it would velocity, magnitude, it won't show it on the surface. Sorry. If you keep it at static pressure, it won't show it on the surface anymore until you hit show results. And then for traces, you can either, and you have to, in order to move objects, you need to reduce them out by selecting within the results. So as you work through here, that's how you kind of clear up and make edits. And then you can change it back to shaded. Let's say you just want this model, or you want a plane, add a plane. Then you can modify the direction of the plane.
yeah. It should also be in the legend options. Maybe when you right click the legend.
I can't tell if it's glitching out on me, but the object disappeared when I added a plane.
Yeah,
Maybe.
that's
Okay, cool. I guess that's something that you'll notice is that it gets quite glitchy because it's a complex system. So you'll find these random errors and you have to find out ways to resolve them. In this case, I just brought it back to shaded and it was visible again. Ken, how do you do it?
I think it's in the legend option. So when you right click legend, it's options and user specified range,
Yeah.
and then you can set the minimum and maximum, because otherwise it's gonna set it automatically, and you might have two different geometries and it sets a different range for both of them. So you can't compare the results if the ranges are different. So if you want to get comparable results between different tests, you set your own ranges, so you get accurate results across the board.
Cool. Thanks, Ken. So I'd like to get a section where the grid with the particular wind speed at a specific point that's on comfort studies. So now that you have the object and you do in a certain, you can do a specific way of, the traces you can do at a certain point along the object. Okay, now the globe has disappeared. But you can add the traces. No, it's not doing it. It's glitching. I might have to reload it. But anyway. You can be specific about where you place. If I understand your question, you're asking about specific locations of placing the analysis. You can pick certain areas and focus on that. Man, it's really glitching bad. And then if you want to export it, you can export the graphic itself through results. So you can animate it, or you can set a resolution and then export out a PNG. And it'll give you a clean screenshot of within the folder that it provided. And you can also modify the color in the background. Okay. I believe that covers the basics of how to do a wind analysis or a water analysis. If you want it to be more like wind or deep water, I think this was another, like the branching is a good example of this. So let's bring it back to a normal velocity and show that as a color. So this branching would be in deep water. So it would show it with lots of traces, but you can also interpret it as wind flow through an object and it reads as fine. Oh, I see. Now I understand your question. So you can do a plane and the plane will make a clipping object. When I attempted it last time, it's acting a bit strange because CFD, like I said, is heavy. And so it gets complex, but I can show you like now it's reading properly. So you can still see the object and it does a cut through it with the analysis on the surface. Ken, you're muted.
Yeah, you can also get a horizontal plane to get like a plan view reading.
Yeah. Oh, numerical data. Have you exported numerical data from?
Never have I ever, but there must be a way.
There's definitely a way because CFD is a very technical program. I think for us in the BioAD field, it's a little too detailed. We were more focused on the design and development of organisms. So I know for sure there's a way because CFD people use it for material manufacturing and development. So I think that's a simple Google I can get into. Maybe when Ken is going through his analysis, I can look through and find that answer for you. It wouldn't be a problem. Yeah, I think I covered CFD. Do you guys have any more questions before we move over to Ken's solar analysis? I know I'm kind of doing this pretty quickly too. There's probably going to be a lot of questions when you guys start practicing. And you won't have the recordings yet, so I kind of get it. So we'll be here though. We'll be able to be helpful. All right, Ken, I think I'm gonna let you do your thing.
Yeah, for sure. I'm gonna share my screen then. Where do I have the presentation? Okay, here. Nice. Perfect. Okay. So Grasshopper solar analysis. We're gonna do a quick rundown of a very simple script to do solar analysis and also to get some wind information and some sun path information from Grasshopper. And I also gonna use this as an excuse to introduce Grasshopper, which we're gonna use tomorrow for the fabrication lesson. So I know you guys are all excited with CFD and Houdini, and Grasshopper is like the less cool cousin of Houdini. But I'm a fan of Grasshopper. It makes sense. It's what it lacks in bells and whistles, it makes up for in reliability and precision. This is what like the Grasshopper interface looks like. You have the Rhino on the back. Rhino is basically where you visualize everything. And this window to the right is the Grasshopper interface. It's a node-based coding platform, very similar to Houdini. The main difference in the way that it's presented is that Houdini moves from top to bottom and Grasshopper moves from left to right. And you have two main node types. You have this node type, which is called a container. It contains information. You can load information from Rhino, from your 3D modeling interface. You can load it into these containers. This is a point container, for example. And you have nodes that perform mathematical or logical operations with this information. This is a very simple node, a line node that takes two different points and draws a line between these 2 points. Usually you have the input of information on the left and the output of the information is on the right. That's generally speaking how it works. And through the connection of a bunch of these nodes, you can get quite complex geometries and you can perform a lot of interesting operations. We're gonna do a solar analysis script today. The files are on the folder that we shared with you guys. I'm gonna open my Grasshopper interface and you guys can let me know if you're ready to follow. Okay. It should be good, right? Are most of you guys here on this? This is I gave you two different sample files. One was the Rhino file and the other one was the Grasshopper file. So, okay, I'm gonna start as if I didn't have this open. So this is Rhino. You open up Rhino, you open you start opening a new file. This is the file that I posted for you guys on Google Drive. So you open the file. Rhino's interface, quite similar to AutoCAD, if you're familiar with that. It has a top view, front view, right view, perspective view. This has a weird name. Okay. We're gonna go to the perspective view for now. And to open Grasshopper, you can either type Grasshopper in the command line, or you can click on this tiny green button. And I'm just gonna close this as if it weren't open. You can open the location of your Grasshopper file. In this case, the one that I gave you guys is called radiation analysis script, and you open your Grasshopper file. So even though Grasshopper piggybacks on Rhino's platform, each file has its own file type, So when you're working on a project that has elements both in the Grasshopper, both in the Rhino interface and in the Grasshopper interface, it's important to save both. Okay, so I'm just gonna check the chat just in case anybody has asked anything. Okay. Cool. I think we're okay. So, so we're gonna start. In this case, we're gonna think that we already have a geometry that we wanna get some solar radiation information from using Grasshopper. So I have set up some containers here. Initially, if you have a new geometry, these containers will not have any information in them, so they're gonna look orange like that. Whoa, my mistake. Clear values, perfect. So I'm gonna start with this geometry. I'm gonna select it here on Rhino, and we're gonna just start with this geometry section. For now, we're not gonna see the context section. I'm gonna explain that later, but we're gonna start here. These geometries are polysurfaces, which for the purpose of Grasshopper are understood as BREPs. BREPs are boundary representation geometries. Basically, for example, on Houdini, we've been working with a set of mesh geometries. These geometries, the computer understands them from the information of each of the polygons that make up that geometry, right? It's like when we have a photograph and the computer breaks it down into a bitmap, then the bitmap is basically the information of each one of those pixels. It's kind of similar when we're talking about meshes. The computer basically collects information of each one of those polygons. When we're talking about BREPs, the computer understands them as basically geometries defined by mathematical equations. So for this geometry here is not a mesh. Basically, it is probably defined by the computer from the equation that defines this this curve, the bottom curve, and however it processes the twinning between these two geometries. So boundary representations are like vectors. They don't really have a scale. You can scale them up and down. They don't lose resolution because they're not pixels, so to say. It's that's kind of the analogy. So we have our polysurfaces and we load them into our BREP container by right-clicking and selecting set multiple reps. So from that point on, these geometries are going to be loaded into Grasshopper. So I can hide this in Rhino. I can select the hide command. They disappear from there. And if in any node in Grasshopper, you can turn on or off the visualization. This one is turned off right now, but if I turned it on with this head here, we're going to be able to see it as a projection of the information that's in Grasshopper. It doesn't exist in Rhino. I can't click it. I can't select it. I can move it. It's not really there. It's just a representation of the information that's here in Grasshopper. About the things that we're gonna be able to see in the Rhino environment from Grasshopper, there are three options here. This is the full visualization. This is kind of a wireframe. It only shows us the wireframe of the geometry, and this one hides everything completely. There are a few options here. The most useful one is this green one. That one only shows you the node that you're selecting. So right now I'm selecting this one, so it's going to show me that one. But if I select the mesh one, this is a mesh container, there's nothing there, so nothing's going to be shown. So that one is also, I use it a lot. It's quite useful. For now, we're just going to leave everything shown, and I'm going to turn off the visualization for now of this thing. So I'm going to show again my geometry Rhino. Perfect. So
Ken, sorry.
yes.
Do you mind reminding everyone what's the hotkey of the viewport?
The hotkey of the viewport.
Sorry,
So right now,
to height
we're in
and
there's no hotkey really. You just type in the command section height, like that, and that's it. And show, it's the same. You type in show, and it's gonna show all hidden geometries.
No, I mean in Grasshopper, if you want to show the VREP or height.
Okay, yeah. You click the scroll wheel, and it's gonna show you this wheel where you have a lot of options. For now, we're just gonna use the disable preview or enable preview option. You can also right click on top of the node, and the preview is here. You can enable it or disable it. For now, we're gonna leave it disabled, but it's either right click or you click with the wheel of your mouse. Yeah. So right now we're working with the VREP. So this thing, we're gonna set it to VREP. We are gonna load our geometry here to this node, and we can already get information from this script. The simplest thing that we can do is get a wind rose. You can turn it on and off with this button that I've set up here. And that gives you wind direction and intensity information. That's basically it. That's the wind rose. And you can also get sun path information, which is the path. Basically, yeah, as the name says, it's the path of the sun in the period that you have set up for your analysis. The period is set up here. We're gonna go to that in a second. So those are two very quick things that you can get from this script. You can change the scale of the sun path representation with this slider here to whatever works best for your project. And finally, we get to the solar radiation simulations. So we started here on the left with the input. Here we're gonna input our geometry. And the other two types of input are the location of our analysis and the time of day and the hours of the day, right? So this location we're gonna get from an information repository that's online. The link is on the Miro board, but I'm gonna put it in the, this is the link. I'm gonna put it in the chat so you guys can have access to it. Where's the, okay. We're gonna go to chat, here we go. Yeah, I'm gonna put it here. Okay, so that's the link to get the location information for your project, right? So in the Rhino interface, it's gonna presume that the x-axis from the top view is the north and the y-axis from the top view is the west. So whichever way that you set your geometry, you have to do it presuming that this is the north and this is the east. Yeah, so right now the location that's set up here is for Lima, but the workshop is supposed to be set up on London time, so we're gonna do the process of changing the site. We're gonna search for London. So this is the page. Energy Plus is a program for energy and climate analysis for engineering companies and architecture, etc. We won't be using that program. We're just gonna use the information that they thankfully have put out publicly. So here we can search for London. And it's gonna give me multiple options for London, whichever one is okay, because as long as it's the same region, it's fine. We're gonna select London Gatwick, I guess, and it's gonna give you a few different options or download all. We're gonna right click on download all, select copy link address, and we're gonna paste that here. And that's going to change the location of the analysis. So now our windrows is going to look quite different because it's a completely different location. This is the information for London, not for Lima. And the sun path is also going to look quite different because London is much further north. So the sun angle of incidence is going to be quite different. So yeah, this thing is set up to automatically give you the information according to the location that you set up in this input and also in the hours. For now, let's say that we want to run an analysis on the summer months in London. So from January to, I don't know, to March, okay, to the end of March. The whole month, so from day 1 to day 30 of the month, and from 8 a.m. to 8 p.m. Let's say that that's our area of interest. So that is set up, our location is set up, our geometry is set up here. We already got our information on the sun path and on the windrows. This can be exported. I'm going to show that later, but let's go to the solar analysis for now. This is the grid size. The grid size is basically the resolution of the analysis. The smaller the grid size, the heavier the operation. So it's gonna take a little bit longer to compute. This analysis is not running right now. To get it to run, we need to double click on this button. We leave it off usually to change the parameters because it usually takes quite a few seconds to calculate. And if we were to leave it on at all times, each time that we make a change either here or in the location or even in the input geometry, it's going to take us a long time to compute. So we were interested in only having to run these calculations once everything is set up. So for now, it's turned off. We set up all of our different parameters and then we get it to run. So we double click and it's gonna take probably, oh, we got an error. What did we get? Oh, yeah, this is set up. Oh yeah, we need to disconnect that one. My bad, sorry. So we disconnect that one and it should, yeah, okay, now it's gonna run. It's gonna, as I told you guys, it's gonna take a few seconds, and the smaller you make your grid size, the longer it's gonna take. Okay, so now it's looking like that, kind of dirty, but that is happening because the results from Grasshopper are superimposing on top of the geometry that we had in Rhino. So now, for now, we're gonna hide the Rhino geometry. Now we get a clean result. So as you guys can see, it's giving us quite a bit of information on the sections of the geometry that receive more or less sunlight. We have a legend here to figure out the boundaries or what each color amounts to. In this case, we're running a simulation on direct sun hours. So hours of direct sun that each one of these points of analysis are getting. So we're getting, well, yeah, the blue areas are 0 hours of direct sunlight, and these light orange areas are probably around 800. Now, we can also alter the boundaries of this legend, and that's also going to alter how the colors are represented. Right now, we can see that we're not getting any point with 1,000 hours of sun. So if we want to get a more nuanced graphic on these temperature changes, we can shorten this range. Let's say we get the top of the range to be 800 or 900. Okay, let's get it at 900. Well, before making any modification, we turn it off. We set this. This is the legend parameters. We can set this to 900, and we can run it again, and it's gonna give us basically the same result, but the color gradient is gonna be slightly different. Okay, yeah, we're getting a little bit more yellows, and on the kind of you can see the path of the shadows as well. These sections that are getting much less sun. Yeah, and this side of the building is definitely gonna remain darker, because if we look at the sun path, and we already commented, most of the sunlight in London is coming from the south hemisphere, so it's reasonable that we would get darker areas to the north. So yeah, that's basically the logic behind it. There's a different kind of simulation here, which is radiation simulation. It's slightly different because it's not the hours of sun that are hitting the geometry, but it's the radiation that's hitting the geometry, which is a slightly different concept. It's generally used more for a solar panel design. It gives you interesting information if you're working with solar panels. I decided to include it because maybe some of you guys might be interested more in the actual number of radiation than sun hours. It's up to you. And as you can see, I run the simulation and I'm getting all blues. That is happening because before we were talking about hours of sun. Now the unit is not hours of sun, it's kilowatts per square meter, which is a completely different measurement. So this range of 0 to 900 is not realistic, because it's not going to get 900 kilowatts per hour per square meter. So we need, whenever we change the analysis, we need to also change the parameters. So let's say that in this case, we want our upper limit to be 200. Okay, so we're going to put the upper limit to 200, and we should get a bit more colorful of our result from this. There we go. Okay, so that's a little bit more reasonable. Again, this is a different kind of information. This is radiation, not hours of sun. I'm gonna check the chat for a second. I have some old label. Okay, yeah, sorry. I might be working with an old version of Ladybug, but if you use the old version or the new version, both should work. Oh yeah, I'm running Rhino 7. Yeah, force of habit. But yeah, script should still work even if it's the old version. If some things are not running for you guys, I would disconnect the context. Just right click, disconnect. Oh well, nothing's connected right now. Yeah, just disconnect the context. We're gonna get to that in a minute, and just work with the geometry node. For now, I'm gonna let you guys into the context thing in a minute. Okay, so that's the general analysis. The thing is, you guys are gonna get your geometries from Houdini, so you're gonna be working with meshes. So meshes are slightly different in the way that you don't get to change the grid size, because it's gonna allocate the information to each one of the polygon subdivisions of the geometry. So whatever polygon count you have on the geometry that you put into this mesh container, that's your grid size. You're not going to be able to change that. So you have to be careful on how dense you make your geometry for this analysis. The same as in CFD, that you can't input too heavy of a geometry because the program just crashes. Same consideration goes here. So we're gonna input these meshes into this container, set multiple meshes. I'm gonna select the mesh input here. I'm not gonna touch the context for now. We're gonna get into that later. And I can run the simulation. It's gonna take a few seconds. I'm gonna check the chat. Failed to fetch packages from sources package manager. Have you tried, and Bala, I'm answering your question. Have you tried checking the link that I left on how to install plugins in the brief, in the PDF file that said brief? There was a section on how to install plugins. That might help. If not, let me know and we can check it out. Okay, yeah, it's taking quite a bit of time. Maybe because I'm also streaming. Okay, so this is all yellow because the legend parameters are too high or too low. So it's reaching the upper limit quite easily. So I'm gonna turn it back to 1,000 here. 1,000, and it should be able to calculate this mesh. It's gonna take a second though. So right now, what the program is doing is it's showing us a graphic representation of these results. It's giving us a legend, and it's giving us like surfaces and colors to kind of let us know how many hours of sun or kilowatts of energy are hitting these geometries. There is a way to get all of this information, same as probably the question was on CFD, and to analyze a specific point of the geometry. Now, okay, I'm gonna check the chat because I saw a couple of messages coming in. Yeah, that's the one. Thanks, Walter. Okay, cool. So each of these results are being analyzed as a set of points. There's a point output to this. This is the node from Grasshopper that's doing the solar analysis, and it has a set of outputs, right? One of those outputs is this mesh that we're seeing right now. If I don't select it, it doesn't show it. I'm actually gonna hide the Rhino geometry. Okay. So this is the geometry that we're seeing, this mesh node. That's one of the outputs of this analysis. We're also getting a point cloud. I'm gonna turn this on for a second. We're also getting a point cloud, so a cloud of points, and a set of data to each one of those points. So the data, the amount of hours of sun per geometry is related to a point in the geometry. So these are a lot of points. So to find one point in a list that long is quite difficult, I would say, or at least tedious. It would be tedious to find the right point for the place of the geometry that you want to analyze. So the method that I propose is to send a probe, like send a spaceship out in this Rhino universe to to kind of find the location that we're interested in. So our probe is going to be a point. I'm going to create a point here in Rhino, anywhere, basically. This is our point. And like any geometry, you can move a point almost freely with this tool, which is called Gumball. It's down here, Gumball. If you don't have it activated, I recommend that you do. It's quite useful. So you select your geometry and you press Gumball here, and you have basically the 3 axes to move your geometry in this space. So, whoa. So we're gonna put this point into the Grasshopper interface, into this point container here. So I right-click this point container, I put set 1 point, and now this point is related to this piece of container here in Grasshopper. So if I move this point close to the geometry, what this piece of script is doing is it's finding from this cloud of points which point is closest to the point that I'm using. This 1 point that I configured as my probe. So the closest point in this geometry, it's gonna find it, and it's gonna let me know the coordinates of that point and the amount of sun hours. In this case, it's 742. So let's say I'm working with an organism, a plant that needs in the summer less than 200 hours of sun because it's very sensitive to sun. Okay. And I might be interested in these blue sections of the geometry. I'm gonna go down here, for example, and from the reading of this point, I get 335 hours of sun. So I could say, okay, this is the appropriate space for that particular organism. Or I don't know, maybe I'm working on a building in a very arid place, and I need to protect some wall from excessive solar radiation. I can potentially see with this tool what kind of shading elements could help with producing this shade that I need. So this little point, this little probe is going to help us get detailed information that we're kind of also getting visually, but we can get a more detailed reading by analyzing portions of the building. And the final thing that I have to show you, this is useless for now. The final thing that I have to show you around this script is also using context. So context is any kind of geometry that's actually, I'm going to try to answer some questions before finishing this thing. Okay, we're still talking about the plugins. Okay, we can check that later. Okay, context is any kind of geometry that you want the program to consider to calculate the shade, but you don't need any information on the object itself. For example, in this section, in this model, I have a few trees. Now, I want the program to consider the trees to produce shade, but I'm not interested in knowing how much sun is hitting this tree. So I don't want it to be part of the computation. I don't want to get all of these color thingies on the tree. I just want the tree to be considered to produce shade. Okay, so in this case, these trees are meshes. I'm gonna load them all into the context section, into the mesh container. I'm gonna select mesh. And I disconnected earlier because it was messing with the calculation. But I'm gonna connect it here into context. Here, into context, again, you connect everything that you don't want to be considered as an output of information, but you want it to be considered to produce shade. So we're gonna turn that on again. And this is also important. In this case, we're using a tree as an example, but this is also important in, for example, in a city, when you're analyzing one building and you have buildings around it, but you don't want to know, you have no interest in knowing on the output of information from those other buildings, but you want them to be considered because they are producing shade on your geometry. Then you load those external buildings as context, and you analyze the information on just your target geometry. Okay, so now we can see, well, I'm gonna show the trees again. Yeah. So in this case, we're not getting this color-coded information on top of the trees, but we are getting information on how the trees are producing shade, potentially even shade on top of the geometry. So that is also useful in case you guys are interested in something like that. I think that is roughly it. Does anybody have any question? Is it all clear? Cool. Okay, I'm gonna post this. I think I made a couple of modifications to the Grasshopper script, so I'm gonna repost it into the into the Drive folder. Just remember that if you're not using any context, you probably want to disconnect it, because it's gonna, if the container is empty, it's gonna mess with your calculation. It's gonna give you an error. Yeah. Other than that, yeah, just how do you inform based on the results from the simulation? Also, do you use an evolutionary plugin for iteration? You could use an evolutionary plugin. I think Anemone is the most well-known plugin for Grasshopper for evolutionary iteration. In this case, it's not really an iterative. Oh, I see what you mean. That, like, getting information out of Ladybug and implementing it into an iterative evolutionary algorithm. That would be super interesting, although I would presume that it would be computationally heavy for Grasshopper, because you see how much each one of these computations takes. And the more complex your shapes, the longer these calculations are going to take. So I'm not sure if it's super adept for an iterative algorithm. It might crash your computer. But it's an interesting thought.
Yeah,
And
I think sorry, I was just gonna say, I think for informing your design, typically that comes from research on if there are certain parameters that you need to be within, or certain things that you're going for. Like, for example, when I go back to thinking about the project that I worked on, there was speeds of the water conditions that we were looking for that were effective for protecting the tide pools. So once it got to a certain reduction in speed, then I thought it was enough branching density. So you modify the design based on parameters that you have developed through your research.
Yeah, for instance, if you were working with a particular plant species that requires a lot of sunlight, with this tool, you can maybe find sections of your project that are more adept to having that species, and you have a different species that have different requirements, maybe low or medium levels of sunlight. You can find those numbers in research papers, or I don't know, encyclopedic knowledge, I'm not entirely sure. And you can get the information from the simulations to be like, okay, I know this is going to work here because I have the numbers and they match, you know?
Okay, great. I think we should give them some space and time to work on their projects now.
Yeah. Yeah, so we're gonna allow for some time for you guys to work collaboratively. I would say try to see what's more beneficial for your project, because we have shown a lot of things today, and it doesn't mean that you have to use everything right away. Maybe for your project or your team, it would be more beneficial to right now talk about the modeling and ask us questions about the modeling. Or maybe for a different project, one of the simulations might be more important, so you might want to focus first on that. Or maybe in some groups, if you have a lot of people, I don't know, you can separate on tasks and be like, okay, you two guys work on the modeling and we're gonna try to run simulations. Depends entirely on you. You can also ask us for comments or recommendations, and we're just gonna be here. We're gonna open the rooms again. Let me just check how many rooms we need, because I remember that
7.
I guess we need like 7 rooms, right? Okay, I'm gonna set up 7 rooms. You guys know already what group you are in, so get on your respective rooms and yeah, ask us anything if you need to.
Yeah, just focus on the I think being aware of what computational method is best for you is important, like having that conscious choice, and then how you use them. So focus on the simulation and what you're learning from it. And through that, you'll find a way of analyzing and evaluating that makes the next iteration and helps you understand the environmental analysis a bit more strongly. Have fun. We'll be here.
Yeah, I see the question about if you feel like you are interested in exploring the solar simulations right now. Yeah, for sure. The script is already loaded in the Drive folder, and I'm loading also the one that I just worked with you guys. It requires the Ladybug plugin, and it can be applied to any geometry. You just load, if your geometry is a mesh, just load it into the mesh container and go from there. Or if your geometry is a polysurface, a VREP, then you have also the appropriate container. So yeah, the script can be applied to any geometry, or at least it should be applicable to any geometry. If you run into any problem, let me know and I'll give you a hand with it. Cool.
You're muted, Ken.
Okay, great job, guys. I loved seeing
Yeah.
your progress on Miro.
Cool. Then as soon as we finish this thing, I'm gonna download the recording from Zoom, and it should be uploaded in the next 3 to 4 hours. Yeah, as soon as possible. So yeah, good luck to you guys. We're super excited to see what you guys come up with, and we'll see you tomorrow.
See you. Bye.
Thank you.
Cool.
Cool.
Thank you.
Take care,
Bye.
guys. Bye.
Mhm.
See you tomorrow.